Okay, there we go. Hiya. So, one of them we know already. We know we've talked about this. We actually proved it once. There is one identity for sure that we know. Come on. So let's kind of develop it again real quick. If I'm given a triangle, a right triangle, can somebody tell me the relationship between X, Y, and R? What relates X, Y, and R? Some old dude? Yeah. So I get what now? I get yeah, X squared plus Y squared, R squared. Now, real quick, what's another way to write X using the angle? So let's see. There's kind of a shortcut to do this. It's going to become very useful in a bit. I think I said this to you guys before, but one way to look at cosine and sine, and this isn't strictly true, but it works in terms of a framework. Cosine theta is the percentage of the hypotenuse that's in the x direction. And sine theta is the percentage of the hypotenuse that's in the y direction. So if I want to get to somebody's house and I go over and up, well, that trip had a part of it that was in the x direction and a part of it that was in the y direction. So the percentage of each is determined by the trig function. So here's the slow way to do this. What's cosine theta from the triangle? What's cosine theta? X over r. So then x is r cosine theta. Do you see what I mean? This percentage of the hypotenuse is the x piece. So what's the y piece? No. What's the y piece? Just go straight to the point. No. Why was this one x as cosine? Because cosine likes x. So what percentage of the r is in the y direction? Sine. Now again, we know sine theta is y over r, which leads to this equation, yes? But it's a little bit better to be able to say, if I'm given a hypotenuse, how do I break it in the x piece? I take this times cosine. And the y piece, I take whatever this is times sine. Bam! So I'm more like breaking something down into its x and y parts. Do I know what x and y are here? Yes. X is r cosine theta, y is r sine theta. So Trent, you answered from the standpoint of just a general person. Well, I want to know from the standpoint of an algebra student. Yeah, x is r cosine theta. Can I rewrite this then? What do I put in place of x? What do I know x is? R cosine theta. And what do I put in place of y? So what do I get? I get r squared cosine squared plus r squared sine squared equals r squared. Do you guys see how I can divide by r squared?
Yeah.
Now, does this equation look familiar? Or this is actually an identity. It's not really an equation. The reason we call this, does this look familiar to anybody? I'm certain it's come up once or twice, but I don't know if I made a big deal out of it. There you go. So, this, we call it an identity because it's not something I have to solve. It is just a statement of fact. If I said 1 plus 2 equals 3, is that an equation? No, it's an identity. 1 plus 2's identity is equivalent to the identity of 3. That's an identity. So that is just a statement of fact. Not your problem to solve. It's just a statement of fact. Now, the way I normally write it is I start with sine just because sine is like our first little dude we talk about. Same thing, right? But I know I'm going to write it like this. I just turn it around. Can you guys take a minute? Has everybody written that down? Can you all just divide each piece of that by cosine squared? Just for fun. Divide both sides by cosine squared, because we're allowed to. And that means divide each thing by cosine squared. Let's see what we get. So right here, what's cosine squared divided by cosine squared? 1. What's sine over cosine? So what's sine squared over cosine squared? Tangent squared. And what's 1 over cosine? So what's 1 over cosine squared? What's 1 over cosine? Secant. Yeah. Remember, C goes to S, S goes to C. There is a second identity that really isn't its own identity. We can get it from this guy, but it's still an official identity. By the way, what angle is this true for? Every angle. Kick ass. So I don't care what the angle is, as long as it's the same. So if I said, what's this cosine squared of 11.3 degrees plus sine squared of 11.3 degrees, and you have to do it by hand, some students go crazy. You guys will write, what's cosine squared of 11.3 degrees plus sine squared of 11.3 degrees? 1. Done. Sweet. Kick ass. Yes? That is a little bit evil, and I don't care. Because you have to get used to these identities and look for them. So one big thing we're about to get into is we're going to get into verifying identities. Which is kind of like, not to put too big of a thing, it's kind of like a big milestone for students because it's the first place where you understand that part of doing a problem correctly is doing the wrong thing first. Because if I have multiple ways I can go, how do I know which one is right until I eliminate which one's wrong? So if I choose to do something and it leads me somewhere, I'm like, oh, don't go that way. Let me go back and go a different way. Not a big deal. Doesn't mean I don't know shit. It just means I do know shit. I'm trying stuff. Leave me alone. You guys kind of with me? So students are used to playing with stuff. And I don't blame you because you're like, I don't even want to do math in the first place, Jeff. I want to play with it. But the more tools you have, the more you can condense stuff. In trig, where does it show up in the real world? Everywhere. Trig shows up everywhere. You have no idea. So the more I know how it interacts with itself, I can simplify shit in the world that I have to try to solve. Okay. Or I can understand the software that solves stuff for me, and I can understand when it makes a mistake. Now, if I go back a step, there's a way to get another identity. Does anyone see how to get one more identity out of this thing? That's insane. So everybody, divide by sine squared, because Trent said so. So everybody try to, just like we just did, divide each piece by sine squared. You get something kind of nifty. So let's see, I get a 1 here. What's cosine over sine? So therefore, what's cosine squared over sine squared? Cotangent squared. And then 1 over sine must be the other dude. Yeah. So do you see the analogy here? The tangent squared plus 1 is secant squared. cotangent squared plus 1 is cosecant squared. That kind of kicks ass. There's a beautiful symmetry between those two, which is great because we have to memorize all three of these. Which some of you guys might realize, just memorize this one and create these as you need them, right? It's up to you, however much brain space you want to devote to this. Yes?
Can I just see the rest of the paper?
Yeah.
Just like...
Oh, I can't zoom out anymore. Okay. Cool. Okay. So let me do this. How many of you guys have your lecture book? Somebody need to borrow the packet of what we're going to look at. And finally, going back to this poor little purple book. Oh, that should be. Everybody else good? Okay. You want one, Christy? Yeah. Okay. So go to module 13. Lucky number 13. So you'll see at the top, they put some old stuff up here. This is all stuff we already know. And then they put the ones we just discovered. And you can tell, why do you think we call them the Pythagorean identities? That's insane. Okay. So the main one is based right off of Pythagorean theorem, and then the other ones come from it. So they're all the Pythagorean identities. So here's what one level of this could look like. So example 1 is not verifying an identity. It's just saying to simplify it. Does anyone see anything you could do to simplify that? Example 1.
Secant squared on the bottom is equal to 1 plus e.
Okay, beautiful. Okay. Trent, just to let you know ahead of time, that's the wrong way to go. But we're going to go there because it's almost too beautiful. It's almost like I told you ahead of time. Say this. But it's a good idea, and there's not a damn thing wrong with this idea. You just realized that secant squared is 1 plus tangent squared, right? Okay. But where can I go from there? I cannot break this shit up. Ain't no way in hell. Because this is being divided by all of this. Now, if the bottom was 1 term, but the top was 2, then I could break that shit up. Yes?
Yeah.
So there is potentially a way to do what you just did in reverse. Can I replace the top with something? So one of the first levels of the simplification or verification of identities is, do you see anything squared? Because we have 3 freaking identities that all relate squares and trig functions, yes? Yeah. So when I see these things and I see a square, it doesn't mean I'm going to use one of those 3, but it means I should try and see if it gets me. So we just tried. It was a really good idea. That didn't get us anywhere. Good. Are you guys really cool with that? You cannot break this up. You can't. Because this is being divided by this whole thing. Yes?
Can you put the 1 over to the other side? Secant squared minus 1.
Totally. So the funny thing is, this isn't just 3. It's more. Because if I subtract 1 from this one, that means that tangent squared is secant squared minus 1. So now, instead of going this way, I realize that this path is no good. It was one of the paths I could take. So I had to go down that path for a second and go, I don't want to go that way. Then you back up and you go, well, I might have had an idea. Why don't I replace the top? Is everybody really cool with this? If 1 plus tangent squared is secant squared, and I subtract 1, then tangent squared is secant squared minus 1. So wherever I see tangent squared in the universe, if I wanted to, I can replace it with secant squared minus 1. Now, why does this work differently? What's being divided by secant squared? Secant squared and negative 1, yeah. So that I can break up. If the bottom is one term, I can break it up. So what is secant squared divided by secant squared? It's kind of just like undoing, like somebody got like denominators and we just broke it back up. That's why this works and that's why that does not work. Secant squared divided by secant squared is 1, that's crazy. And what's 1 over secant squared? Secant is cosine. Now, there's one more step you can take. Let me stop for a minute. This was just us exploring options. Yes, I took this and I rewrote it so I solved for tangent squared. Are you guys understanding? The minute I have a statement of equality, and I know it's an identity, I know it's always true, I can move things around. And it's not like an entirely different statement of truth, it's just reorganized. So now I can use it in different places. One more step I can do. What's 4 plus 5? What's 4 plus 5? 9. What's 9 minus 4? What's 9 minus 5? So if two things add to be something, that total minus one of them is the other one. What's sine squared plus cosine squared? Sine squared plus cosine squared. So what's 1 minus cosine squared? Sine squared. It's got to be the other piece, right? If I take a total minus one chunk, it's the other chunk. 10 minus 8 is 2, because 8 and 2 make 10 together. So 10 minus one chunk of it is the other chunk. You guys see? Or you could subtract sine squared and get, is that what I want? No, cosine squared. Subtract cosine squared and get 1 minus cosine squared is equal to sine squared. Kabam! Now, just to show you, I'm going to do that problem again a completely different way. So when you're doing these kind of problems, you could pick the wrong first step. That means you're doing the problem right. Because you're investigating paths. That's the whole point of the problem is, hey, you know a lot of shit, try one of them. If that doesn't work, you know some other shit, try some of those. Are you guys kind of with me? I think a lot of students get into this and they pick the wrong thing first. And they say to themselves, oh, I don't know shit. And I'm like, no, you're doing great. You did fantastic. Now you know not to go that way, right? Okay. So, just very quickly, did anyone think of another way to do this before I just show you a different way to do this? The way I'm about to do it is very often a last resort, but since this is so simple, it's actually not that bad. So this is, let me write it weird. Tangent squared divided by secant squared, yes? That's the same problem. Isn't tangent sine over cosine? And isn't secant 1 over cosine? How do I divide fractions? Multiply by the reciprocal. These cancel, I get sine squared. Is it the same answer we just got? Yes, a completely different way, yes? Yeah, it's no problem with that. To be honest, I appreciate that nobody suggested this because a lot of students just always change the sine and cosine, and sometimes that is horrendous. Then you have all this shit going around. No. Look for higher level stuff first. And then go, all right, I don't see anything. Maybe I try to make everything sine and cosine. I see it as more of a last resort if you can't see other stuff. This problem is so simple, I think either way actually is roughly the same amount of work, so it's okay. How you guys doing right now? You guys all right? So I do want you to know, this very often is frustrating for students, but I'm trying to show you why it is and why it shouldn't be. What about this one? Yes, sorry. Oh, sure. All right. Are you cool with this fact? Okay. Which way was it? Okay. If I subtract cosine squared from both sides, and I'm allowed to do that because this is true, this is inequality, what does 1 minus cosine squared equal to? Sine squared? Yeah. It just is. If sine squared plus cosine squared is 1, 1 minus either of them is the other one. So if A plus B is C, without thinking about it, what is C minus B? A. If I take A and B together makes C, C minus either one is the other one. Yes? That happens so often in mathematics. It's really good to just stop and realize, oh shit, there you go. And then these identities, so often we have to kind of like minus and move them and reorganize. If you just realize, so what is cotangent squared? It's equal to cosecant squared minus 1. Okay. What's different with example 2 that tells me, because this is all we really know so far, why can't I use any of those the way that example 2 is written? I don't see any whats. Those Pythagorean identities, what's true about every trig function that's in them? They're being squared. So that's why in the first one, that's why I said maybe Pythagorean theorem would work because, Pythagorean identity because it's squared. Here, nothing's squared. What do you think? All right, if I just said, if you were in my algebra class and I said simplify this, what would you do? Yeah. Distribute, yes? Okay. So simplify. What do I do? Yes. And now, what's interesting is, does anyone know what cotangent times tangent would be? What is cotangent? 1 over tangent. Okay, so let's replace that. Cotangent is 1 over tangent. I could write cosine over sine, but you see how that does nothing for me. If I write 1 over tangent, what does this become? 1. Now let's look at these guys. Now these aren't directly related. Do you agree with me? So, I don't see any squares. I don't see any like identities of any sort just kind of jump out at me. So now I'm going to do kind of like the last resort. I'm going to write everything in terms of cosine and sine. So what is cotangent? What is cotangent? Y is cotangent. What is it? Who over what? In terms of sine and cosine. Yes. And what's secant?
1 over cosine.
Yes. And what happens? What happens? What happens? No. Don't overthink it, guys. No. What's 4/9 times 1/4? What do the 4s do? So what do these do?
Cancel.
And what's 1 over sine? Cosecant. Jaboo. And since it's not squared, I can't go one more step there. I can't do anything else. Do you guys start to get a feel for this? Unless I can see an immediate reason to go to sine and cosine, or normally do that as a last resort. If I see squares in the problem, I think, oh, let me see if an identity would do something for me. It won't always. Or I'll pick the wrong thing, which is fine. That's part of the process. Let me stop for a minute. Now, I always want to address at some point the fact that I know somebody in here right now sitting there going, okay, what are we doing? Why are we doing this? But how long ago did you learn about like 4x? How long ago would you estimate? Was the first time you ever worked with 4x, for example? Something like 4x? 9 years ago? Okay. Some of you guys is like, it's quite a while back, yes? Okay. And during that time, you've learned how to distribute it, you've learned how to add it to other stuff, you have learned how to divide by it, you learned how to whatever, yes? Even this semester, we learned how to long divide some of this shit, yes? How relatively long ago did you learn trig? Not very long ago. So, when you first learned something like 4x, 3x squared, 5y, you have to learn how it interacts with other things that look like it. Yes? You have to learn how to FOIL, how to distribute, how to divide, how to all do all this shit. We are doing that now. Because we only recently learned about trig. And now we're trying to see, well, how does trig interact with itself? Oh shit, here it is. We're trying to see what it does with itself. You guys got it with me? And why do we do this? Has it been useful to you to know how to do 4x plus 5x? Has that been useful at all?
Not yet.
What do you mean? You haven't had to do that at all to get to where you are now?
Oh, in math.
Yeah, of course. But of course, your entire math career is hopefully going to get you to a field where you're going to be applying the mathematics.
Right.
And I've already tried to show you some situations in real life where you apply some of the stuff. Okay. So you're in a class where you're still learning how these things just interact with each other on a very base level. So we're doing like really, really basic shit with more elevated ideas. We're just, okay, here's trig, which is up here. How do you do the stuff we did before with other things? Can you do that kind of shit? So look at example 3. Does anything jump out at you? Are there like terms? Are those like terms?
Yeah.
Are they? If this was sine cubed theta plus 2 sine cubed theta, that would be 3 sine cubed theta. Yes? Because I'm keeping track of how. Do I have any more sine cubed thetas besides that first 2? Nope. Do I have any cosine squared sines besides that second 2? Nope. So do I have like terms? No. So what the shit can I do? There's only really one thing I can do here. And there's no immediate equivalent thing. There sort of is, but it's a little.
You can change cosine squared to
That would work. It would be different than what I'm thinking, but it would work, yes.
Divide by sine.
Now, real quick, Dylan, I love that idea. The only issue is I don't have an equation.
Oh, okay.
So I'm not allowed to divide. But instead, you do effectively what you just said. So what effectively is the same thing? How do I get a sign out of them without dividing by it? I just take it out. Now, Trent, you're in the right direction to something, so I might come back to that. Do you guys see how each one has at least one sign? So what's left here? I had 3 signs. I took one of them. What do I have here left?
Sine squared.
Yeah, 2 of them. And this guy, I took his sign. And what is sine squared plus cosine squared?
1.
Sine theta times 1 is sine theta. Done. So all this shit is just sine. Isn't that silly? That's neat to me. Sometimes I have students that are upset. They're like, oh, I did all that work and I just got this. And I'm like, I did all that work and I got something way nicer. I love that shit. Do you guys see how to start looking for things you can try to do? No like terms. Let me back up, because Trent had a good idea that would also work. If I replace, somebody help me out. Somebody who's not Trent. Because you came up with the idea. So I want to help, I want everybody else to explore this idea. What can I replace cosine squared theta with? What can I replace it with? 1 minus sine squared theta, yes. Good Lord, Jeff. What is that? And then what can I do here? Maybe if I underline it. Yes, okay. So I get sine cubed theta plus sine theta minus sine times sine squared is sine times sine squared is sine cubed. What's sine cubed minus sine cubed?
0.
So the answer is sine theta, which is what we got before, yes? So again, a whole other way to do the problem that I really didn't think about at first. That kicks so much ass. Okay, I like it. So even if you haven't gotten to the point where you see how this kind of thing is useful in real life, you know, 4x and 4x is 8x minus 8x is 0, so then I simplify. Okay, so we've done things where we solved semi-real life problems because we knew how to do this. Same thing with trig. Trig shows up everywhere. So the more I know how it interacts with itself, the more I can solve, the more I can handle. Maybe. So now we get to the good stuff. All right. I'm going to do a few of these with you, and then you're going to do some by yourself, which is absolutely amazing. I never do that. Which one do I want to leave for you? Oh, cool. I'm going to leave 4 for you. We're going to look at 5, because 5 is trippy. So here's the idea. Okay, this is a little, let me think. Let me start with one that's not so crazy. You're not too crazy. You're definitely crazy. No, I can't do there. Okay. Shoot. Yeah, okay, look. Let's start with 4. Well, I'll figure out some more for you guys to do. Okay. The whole idea here is this is not an equation. This is an identity I need to verify. So going in, what does it mean to verify something? Does it mean you already know it's true? No. So if you're going to verify something is true, you don't know if it's true. In fact, very often our null hypothesis is it's false, and I'm looking for evidence that it's true. I am not allowed, in fact, here, going back a step. Do you guys really know why you're allowed to, if you have an equation, why you're allowed to do this? I mean, you've done it for so long, you might have forgotten why you're allowed to. Because it's given to me as true.
Yeah.
In fact, we want to know what x has to be to make it true, so we assume it's true and see what that means to. And that's why if I get an answer like 3 equals 4, that shows the assumption was false, it can't be true. There's no solution, right?
Right.
So I am only allowed to add, subtract both sides, multiply, divide both sides, if I know the equality is true. So when I'm verifying an identity, I do not know if it's true. So one of the main things I need you to understand, and do you notice how big of a point I'm putting on this? You cannot do something to both sides. You cannot. So what are you actually trying to do then, right? You guys look even more excited. What are we actually trying to do then? In order to verify this identity, I need to show that one side becomes the other side. So I am all day long allowed to take a side and work with it. And what I'm trying to do is I'm trying to make it look like the other side. So I could pick one of the 2 sides and work, and I hope it's eventually going to become him. Or I could do a little bit with both sides and see if they can meet somewhere in the middle. as long as I can get a chain set up between the two, that would show that it's true. So let's try this out. Which side do you see something you can definitely do?
Sine squared can be changed.
So the left-hand side. So we're going to work with the left-hand side, and what I always tell students is, the side that you see something to do, work with that side immediately. Do what you saw. Something else to notice. How many terms are on the left-hand side? Now I got that song, man. Pass the touchy on the left-hand side. So how many terms are on the left-hand side? 1. How many terms on the right-hand side?
2.
So I'm going to start to introduce elements of this. In order to show these are true, I have to take this one term and make it become 2 terms. That's the only way these could equal each other. Do you guys see that? I could use one side as a clue on what to do for the other side. If I look at it the other way, if I can combine these two somehow to make it one term, I'm going in the direction of the other side. So maybe I'll do this again, starting with the right-hand side. So what can I do on the left-hand side?
Sine squared.
Yeah, you see a square. You immediately think Pythagorean identity. Sine squared is?
1 minus cosine.
And then what can I do? Is the bottom one term?
Yes.
So I'm allowed to break it up? What's 1 over cosine? No. C, S goes to C, C goes to S. What's cosine squared divided by cosine? How many cosines cancels? 1. Is that what the other side is? Did we just start with a side and make it become that side? Do you see what I just did? Do you see how I drew a little line and I put a little check mark? Please do that. I know it seems weird maybe. If you get to this point and you just stop here or you circle it, I don't know if you know what you just did. The whole point of this is to take a side and make it look like the other one, or make them meet in the middle. So the minute you get somewhere, you're like, oh, there it is. Can say there, that's the same, check. That tells me you know what the hell you just did. If I could read your mind, I wouldn't need that. I can't. So I need it. Let's try example 5, and I'm going to give you a hint, and I'm going to want you to do example 6. Example 5 is a exceptionally funky problem. But it's one of the coolest freaking things. And the method I'm going to show you for example 5, if nobody else has a suggestion, if you haven't had suggestions, we'll try it out. Because like I showed you earlier, there are other ways to do things than what I think of.
The right-hand side and the bottom could be changed to post.
No? Is anyone squared? Is anybody squared?
No.
So it can't be a Pythagorean identity. Yeah. 1 minus sine squared is cosine squared. 1 minus sine, who knows? Anybody, any other suggestions on something to try on number 5?
You can break up the left.
Okay, cool. Which side has one term on the bottom? The left-hand side? So you could take 1 over cosine plus sine over cosine. 1 over cosine is secant. Sine over cosine is tangent. Does that look more like this side? Does it look further away from this side? Yeah, I would argue yes. At least this one has sines. Now listen, Trent, I really want you to understand. Not a damn thing wrong with what you say. Suggestion is beautiful. Tears, because the bottom is one term. Give it a try. But do you see where you could even try to go from here? I don't see where to go from here to get there. Is everybody with me?
Yeah.
So if you also don't see it, cool. If you see something, say something. Because maybe I'm missing something. But to me, I don't see a clear way.
Yeah.
So let's back up. So this is a beautiful example of trying something and it didn't work. Great, I'm one step closer to having this problem done because I'm not going to go that way again. Any other suggestions? I think that was the one thing I saw maybe somebody would suggest. Multiply cosine where? No, I see. Okay, so again, be really careful. I'm trying to verify this equation is true, and the only reason I'm allowed to multiply or divide both sides by something is if I already have a true equation.
Maybe on one side.
It's called a property of equality. Is adding, subtracting, multiplying, dividing both sides. That's a property of equality. I'm trying to verify this is equal. So I am not allowed to do something to both sides. Is everybody with me? Otherwise I would agree with you. I would try to kill my fractions, dear God, but I'm not trying to solve an equation. I'm trying to verify this is true. Yeah?
If on the right side you multiply the top and the bottom by cosine, you could get squared.
Okay.
So just multiply that.
Okay. Number one, squares are huge because we have 3 freaking identities that all have squares on the trig functions. So if you can see a way to make something squared, that might go somewhere good. What's really funny is I would do exactly that for a different reason. So listen, what is the whole purpose of this? What am I trying to have happen?
You want them to look the same.
I need to have, I could take one side and make it look like the other side, correct? What does this side have on the bottom?
Cosine.
Does this guy have a cosine on the bottom?
Yeah.
Okay, I really want you guys with me. I desperately want you guys with me. If I really am like, what the shit do I do? I pick one thing that's true on one side and I force it to be true on the other side and I hope things happen. And to be honest, more times than not, something good will happen. Yes?
Okay. Are you able to like manipulate the Trig identities?
Of course.
Like as in like, you know how it's like 1 minus sine theta? Like, you know how usually like if it was a squared, it would be
Cosine squared.
cosine squared. Yeah.
But 1 minus sine is not cosine.
Wait, what?
Alright, watch this, watch it, watch it.
Just repeat what you said.
1 minus sine is not cosine. So 1 minus sine squared is cosine squared. Yes?
Yeah.
Alright. How do I kill the square? I take a square root.
Yeah.
If I take a square root, I have to take a square root of this whole thing.
Right.
Square root cannot distribute. We've talked about that before, right? Like the square root of 13 is equal to 5. You guys remember that? Did I talk about that? Is this true? Is the square root of 13 5? Does everyone agree that's not true? But isn't 13 4 plus 9? And isn't the square root of 4 2 and the square root of 9 3? Isn't that 5? So the square root of 13 is 5. Deal with it. No, that's bullshit, right? That is complete bullshit because the square root cannot distribute across addition because the square root's not based on addition. It can't distribute. You with me?
Yeah.
Now, I don't blame you. Your brain will try to say to you, hey man, just do this shit, man. Look, just take the 2 off and everything's fine. And you gotta go, brain, no, brain, ain't gonna work here. Okay. And just to show you real quick, one kind of sucks, but like, what's 9 minus 2 squared? Let me do something better, watch. What's 25 minus 4 squared? You can do it. What's 25 minus 4 squared? 25 minus 16 is 9, so 3 squared. Is everybody with me? You with me? Now if I take, so 5 squared minus 4 squared equals 3 squared, yes? What happens if I take all the squares away? Is that statement true? Okay, okay. Cool. So, I am stuck. Let me walk back a step. We already said we're going to try, but I am stuck. I don't know what to try. I don't see any squares. I don't see anything. So therefore I say, oh, this guy's got a cosine on the bottom. So let me multiply this guy by cosine on the top and the bottom. And I love that you thought to do that because the top becomes squared then, and then you could use like an identity. So let's see what happens to this side. So now I'm going to choose the right-hand side. The top becomes what?
Cosine squared.
Cosine squared. And the bottom, just do this for me. This is going to be very exciting. You're going to love what we have to do here. So, what is cosine squared?
Sine 1 minus sine.
Yeah, 1 minus sine squared, yes. This is actually good this is happening now because it's going to happen a lot more later. Now this, maybe you don't notice this, but you can factor the top. Isn't the top 1 squared minus sine squared? Isn't the top the difference of squares? You guys see that? Remind me, real quick, just in case you don't see it. How do I factor 1 minus x squared? Good, so how do I factor 1 minus sine squared? And then you see something happening? Everybody with me? So I wrote the bottom again, and the top is broken up. What can I kill now? Die. And did I get the other side?
Yep.
Connect, check, continue. I really hope some of you guys see how that's important. Because at the end, I need to make sure you know why you stopped when you did, right? You just sort of stop somewhere. I'm like, did you get lucky? I don't know if you even know what you're doing. If you do this, I'm like, oh, you know, that side became that side. Check, go. All right, so. To be really honest, if you would have done, here, let me show you this. And then I'll let you guys try out number 6. If you would have done this side instead, it would have been a little bit simpler. What I mean by that is, if I would have multiplied this side by 1 minus sine theta. Then the top would have been 1 minus sine squared, because the middle terms cancel, yes? Which would have been cosine squared theta. 1 cosine would have died. Oops, dang it. 1 cosine, and then I get cosine over 1 minus sine, which is what the other side was.
Right.
Okay. But either way you go. This is a little bit harder because you had to realize you could factor that, which is weird because it's trig, but all you need to be able to factor something, in this case, for example, difference of squares, is a minus, and then the other things are squared. That's all you ever need. I don't care what it is. So let me give you a little hint on number 6, if you haven't started yet. Does one side have 1 term?
Yeah.
Does the other side have 2?
Yeah.
What's the other side made of? 2 whats?
Fraction.
2 fractions. So is there a way to start with the left-hand side and combine those fractions? What would you need to be able to combine the fractions?
Like bases.
Like bases, like denominators. Yes?
Yeah.
Very quickly. Does either of those fractions, well, before I ask this question, does either of these fractions have a 3 in it? Does either of these denominators, have a 3 in it? Doesn't 9 have a 3 in it? You with me? Does either one of these denominators have an 8 in it? No, even though 9 is 8 plus 1. We know inherently I mean factor of it, yes? So let me ask you this question. Does either one of these fractions have a cosine in it on the bottom? No. What do they have? What's the first fraction have? 1 minus cosine theta. So what's 1 minus 5? Does negative 4 have a 5 in it? No! Even though it's 1 minus 5. Okay. The other fraction has what on the bottom? 1 plus cosine theta, yes? That doesn't have a cosine theta in it. What's 1 plus 4? 5, and 5 doesn't have a 4 in it, yes? So then what are they each missing? This is the same thing as like 1/3 plus 1/5. The LCD would just be them multiplied. They're each missing each other. Multiply each one by the other one. Go for it. Try to make an LCD and you get those together. Now, the work involved there probably freaks you out as you think about it, but if you just write it out for yourself, it's not as bad as it sounds. But more importantly, how did you even know to try to do that? Because one side has fractions and the other one don't. One side has 2 terms, the other side has 1. So I know if I put these together, I'm going in the right direction. I have to be going in the right direction. Because I need to make one side look like the other. So let me or Christine know if you need some help. Give that a try. I did. You obviously don't have your lecture book with you, right?
Yeah.
I'm gonna steal the copy I gave you. Because we're doing these. We're doing this one. So, try to see if you can consider some things. We'll go over here in a minute. You do that one. Yeah. Okay. I like that. So here's the idea. Take this fraction and multiply top and bottom by 1 plus cosine. And then take this fraction and multiply by 1 minus cosine. And then they'll both have the same denominator. So it's sort of like, if I had 1 or plus 1, I have to multiply each one by the other one, yes.
because 4 and 5 have nothing in common. So 4 needs a 5, 5 needs a 4. These have nothing in common. They don't. So this guy needs 1 plus cosine theta, so multiply top and bottom by that. This guy needs 1 minus cosine theta, multiply top and bottom by that. Yeah, now roll the bottom and put your like terms together on the bottom. You're almost there. Almost there. Yeah. Oh, wait, sorry. Whatever you do to the bottom, if you do the top also, just multiply top and bottom by 1 plus cosine.
Oh, yeah.
Otherwise, it's not legal.
Right.
Yeah. I did this, let me know if everything was wrong. I have a question. Did I gave it back to you, right?
Oh, yeah.
And on one end, I told you, there's a little bit of one there. Yeah.
Okay.
I mean, basically. Now that one, I'm giving you a chance to review it to get like 4 points back. And that counts as corrections. So, yeah.
Thank you.
Yeah, so far, so far. But now they have the same denominator, so you can put them together. These go together on the top. 1 minus cosine squared is one of the identities. Okay. We're almost there. Yeah. Well, the great thing about these is you know you got it.
That's very
Totally. It's one of some secret. Yes. All right, let me catch up to you guys.
So this problem illustrates a few different areas that students have issues with. These do not share cosine. And then a student will say to me, Jeff, man, I don't know if you forgot one of your meds this morning, but I see a cosine right there, man. But again, does 4 and 2, no, that's a bad choice. Does 5 and 3, do they share anything? No, even though this is 4 plus 1 and this is 4 minus 1. They don't both share a 4, yes? Neither one of them has a 4 in it. Neither one of these has a cosine in it. So what are they missing? They're each missing each other. Aw. So I take this dude and then multiply top and bottom by what he's missing. And I take this dude and I multiply top and bottom by, no, Jeff, what he's missing. No, Jeff, what's happening, man? I don't know what he's missing. So then I'm going to put the whole top all together, all over the denominator, because now they have the same denominator. The denominator is 1 minus cosine squared. Is that cool? If you FOIL out the bottom, you get 1 minus cosine squared. On the top, what happens? And the top, again, I got like denominator, so I'm allowed to add the tops together. Cosines cancel. That's always nice to see. Good to see it go away. 1 plus 1 is incredibly 2. 1 minus cosine squared is sine squared. And then what's 1 over sine? Cosecant. So 1 over sine squared is cosecant squared. Did we make it? Yes, check. So, listen. You have to see what you're allowed to do and what you're looking for until you know how to even try some of these problems out. This one I felt that it would be a little bit challenging because there's a lot kind of going on. But this is one of the most basic things to try. If I see some fractions on one side and no fractions, just one term on the other side, I immediately think, let me get like denominators. Let me just focus on that because that will automatically get me closer. So I have to be going in the right direction. And that's a beautiful point. You know, like that's the only path I should take right now. That's what's going to make them look the same. Okay, maybe. If I don't see that, that's when I'm like, oh shit, all right. I could choose wrong. Let me try something. Okay, that was wrong. Let me try something else. I got fewer things to worry about now. Okay, maybe. So y'all should be very excited about this. I want you to try the next three. And I want you to, can you guys kind of look over all three for a second? Try to see what you would try, and then I'm going to put you into, I'm going to try to group you guys up with one or two other people. Because, as always, there's an odd number of us, I think. Oh, no, it's 8. Wait, 3? No, there's not. I'm not good with numbers. This is 9 of us. Did I say it on the first day? Normally on the first day of class, I'll pass out syllabi, and somebody says, we need one more. I'm like, I'm not good with numbers. And everybody's like, what are you saying? What? All right, go ahead. So, look at these, and then I'll try to pair you guys up with people. Sorry, Ron. Oh, this is what isn't allowed. Like, if my question was 1/3 plus 1/5, I'm not allowed to just only multiply each one by something. So if I multiply this by 5 and this by 3, now my problem is different. I am allowed to multiply by 1. All day, every day, multiply anything by 1. So the thing you forgot was you should multiply top and bottom. That's legal. Because now I just multiply by 1. And when am I allowed to multiply by 1? Any damn time I want to, because it doesn't change the value of something. Same thing over here, right? When we multiply top and bottom. And we know this. If I want to do 5/9 minus 1/3, I multiply top and bottom by 3 to make the bottom become 9. Same thing, same exact thing, just weirder because there's no numbers. There's all this weird expressions. But it's exactly the same idea. Alright, let me see. How about that? Are you getting the head up? Okay. Hopefully you're not leaving visual. Let me help this guy with this counting. Okay. So Christian. Mr. Christian, why don't you work with Ronnie? Come on over here and work with Ronnie. I think Trent, you and Dylan are basically working together, right? Ilion, why don't you work with Layla, and then Ethan, can you come up and work with, where's his name? I always say Layla. So let me know if your group needs help. Me or Shaboo. And then we'll do something very exciting. So this first dude, there's a few different ways to do this. And I'm going to tell you something I don't think I've told you yet. You get high enough up in the math, and one thing I had when I got up in really high level mathematics, I had a sheet of different expressions that were all 1. So if I ever saw a problem where there was a 1, I was like, would any of these, if I put it there, would it make it easier? I don't know if you guys are with me or not. I don't think anyone did example 7 this way. But what is 1 equal to? Sine squared plus cosine squared. So if I wanted to, anywhere in the universe you saw a 1, you could replace it with sine squared theta plus cosine squared theta. How often would that be helpful? Not. Would it ever be helpful? Yes. So I don't think anybody did this, but just to show you, if you replace 1 with what it equals, what do I get? What's cosine squared plus 2 sine, cosine squared plus 2 cosine squared is 3 cosine squared, which is that side. Check! Now, most of you guys, when I talked to you a little bit, you said, I wish that 3 wasn't there. And I said, cool, make it not be there. You can't divide by 3 because you're not allowed to do something to both sides. But you can just rewrite it based on what it means. 3 cosine squared theta is literally 3 of these dumb things. Yes? What is sine squared plus cosine squared? There's my 3 cosine squared, by the way, right? What's sine squared plus cosine squared? 1. What's cosine squared plus cosine squared? And then, of course, you're there. Check! Okay. So, at least 2 different ways to do that one, if not 38. Huh?
Third one, I just changed sine squared to 1 minus cosine squared, so it just...
Ooh! Alright, I'll calm down. So yeah, if you replace sine squared with 1 minus cosine squared, you lose 1 of your cosine squared, so then you have 2 left. Yeah. Kick ass. So at least 3 or 39 different ways to do this. There's 36 other ways we haven't talked about. Same thing goes for this guy. I just suggested to somebody, because I didn't see anybody trying this out. But we saw a problem like this earlier. Nobody tried this except for this one person, but I gave him a little hint. What do both of those terms have in it? Tangent. So can't I factor a tangent out? Now, a really good question for a student to ask is, how do I know when to do that, Jeff? You don't. I don't. I don't know this is going to lead somewhere. I had to think about it in my head to think, okay, if you do that, okay, we'll go somewhere. Will this always go somewhere? Will this always work? No. How do I tell when it's going to work? You try it. Do you understand? So choosing the wrong thing to do is beautiful. It's part of the process. Yes? Do I still do that? Do I have one of these and I have to simplify it and I choose the wrong? Hell yeah. I almost said fuck. Okay. So if I take a tangent out, sorry. What do I get? Cosecant squared minus, take a tangent out, divide tangent by tangent, you get 1. What is cosecant squared minus 1? Subtract 1. Cosecant squared minus 1 is cotangent squared. I know I want it to become cotangent, yes? So let me rewrite everything in terms of cotangent. And then I lose a cotangent. Check. Now, most of us didn't do it that way. Because I kind of went off of whatever you guys saw. And a lot of you guys, and this is beautiful, but this is not the right way to do it. Are you guys understanding? This is not the best way to do it. This is not the way to make Jeff happy. I don't give a shit, right? This is just one way that I saw. Another way is beautiful. Somebody said, oh, I see a square. And this crazy dude that somehow they gave a math course to teach, he said, if I see a square, I think, let me try a Pythagorean identity. I'm like, yeah, sweet. So what is cosecant squared? What can I replace that with? Let me write it over here.
1 plus cotangent.
Yeah, it's 1 plus cotangent squared.
Which can be rewritten as 1 plus 1 over
Sure. It'll be 1 plus 1 over tangent squared. Woof. And then I do tangent theta plus 1 over tangent theta. Yes, is that cool? I'll kill one of the tangents, yes? Minus tangent theta is cotangent theta, which, kaboom! So roughly the same amount of work. So who cares? There's no better way to do this. There's just a way to do it. So this is the looser Mandalorians. There's not the way. There's one of many ways. If you've never seen that's fine. You don't have to have watched Mandalorian to get what I'm saying. This one, I don't blame you. Okay. So there are two fractions. So you think LCD. So I'm going to do that, and then I'm going to show you something else to consider. Specifically when you see this kind of thing, and I'll show you. So if I think LCD, what does this first thing need? What do I need to multiply this first thing by? Sine theta. Good. Sine on the top, sine on the bottom to make it all legal. And then what's the second guy need? Yeah, he needs 1 plus cosine. Really looking good, Jeff. Thanks, Jeff. So then you get sine squared theta over sine theta, 1 plus cosine theta. Yeah, let me just do this. They're going to both have a 1 plus cosine theta sine theta now, right? So I'm allowed to add the tops. This one I've got a FOIL. I get 1 plus 2 cosines plus cosine squared. Okay, now this is a lot, but what is sine squared plus cosine squared?
1.
Plus 1. Holy shit. And do you guys see anything you can do at the top to make part of it look like the bottom?
Take a 2 out.
Take a 2 out. Die. And then what's 2 over sine theta? What's a way I could rewrite that?
2 cosecant theta.
And that is that check. That was a way to go. I know. I did it on purpose. That is a way, not the way. Okay. Now, is there another way to do this? Did somebody do this a different way? And did your way involve waiting until I went over it? So, here's another way to do this. Whenever you have like a 1 plus cosine theta in a fraction, especially if it's on the bottom, you can multiply top and bottom by 1 minus cosine. Why would that be good? On the top, I just get this bullshit. But what do I get on the bottom? 1 minus cosine squared is sine squared. And this, I can split up. Now listen, I kind of went down this in my head, so I'm not even sure if this fully works, but we'll find out. One of my sines dies, yes? Oh my God. And yes, this will work. Oh my God. So then this is 1 over sine minus cosine over sine plus 1 over sine plus cosine over sine. What was I trying to make this become? Oh my God. These die, yes? 1 over sine plus 1 over sine is 2 over sine, which is 2 cosecant, which, just to kind of break through the dimensions, is 2 cosecant. Same thing. Okay. Check. Oh my God. So listen. I need you to really hear this. These are not simple. I have been doing this for 30 something years. I can't remember when I learned this. More than that. Good Lord. What is it? Who cares, Jeff? So of course I know what to look for. I know when to try to do certain things. Good for me, right? You guys are just picking up, so it's fine if you don't know exactly what to do. You're in the stage of, let me try something and see if it works with the shit. So now you're starting to realize, if you saw 1 plus sine theta maybe think multiply top bottom by 1 minus sine theta, because that would force a Pythagorean identity to show up, yes? So you start to kind of collect things I could try. Okay. Yeah. I don't think we have enough time, Christine, to do the big triangle thing. Yeah. So just a little preview of what we're about to get into next time. What I'm really curious about is we kind of know what sine theta is. But is there a way to figure out what sine of twice theta or cosine of twice theta? And you're not going to believe what we call these identities. The math creative geniuses, we said, let's call these double angle identities.
There's like twice in any.
So we're going to prove these, and we're going to do it a very different way than my colleagues do it. And whatever, I don't give a shit. I love the way I do it. It's a derivation we're going to do. You never have to do it by yourself. We're going to develop the formulas. What is, have I announced, what is today? Oh my God. We just took the test, of course. Okay, sorry. I'm doing the same material in my other class, so for a moment I was in the other class. We don't have a quiz coming up anytime soon. Do you guys realize that the final is 2 weeks away, roughly?
Wow.
Yes, I know. Isn't that crazy? Do we have any more tests before the final?
No.
No. We do have at least one quiz. So tomorrow we'll talk more about when that might be. I don't know yet. We'll see. We just started doing some new stuff. Otherwise, that's plenty for today. You guys go out into the world and come back tomorrow. Yes?
Have a good day.
See you. Where did I put it? What have I done with it? Oh, here it is. Okay. This guy?
Yeah.
So I multiplied. So I got an LCD, yes?
Yeah.
This guy's a sine, so I gave the first guy a sine. This guy's a 1 plus cosine, so I gave the second guy a 1 plus cosine. So then sine squared plus 1 plus cosine, 2 cosine plus cosine squared. So just foiling, yes? Sine squared plus cosine squared is 1 plus 1 is 2. Plus 2 cosine theta.
Cosine squared plus cosine.
Cosine squared plus sine squared is 1. Yep. That's why it's not always the right thing to do, but when you see squares, you think Pythagorean identity. And the square in this case came out after we got LCD.